One of the most captivating anomalies of modern cosmology, the nature of the Phoenix cluster, and in particular the galaxy dominating its core, had sparked fascination among astronomers worldwide. At the edges of space and time, a colossal peninsula of islands of light beckoned us to contemplate its majesty. Serving as our only window into that abyss, the Chandra Space Telescope turned its gaze to this site, hoping to understand what was fueling its fury. Like a stellar cradle, thousands of stars were germinating in the depths of Phoenix A, a star formation rate never seen before in the central galaxies of other clusters, which are traditionally dormant, deadlands on their way to eternal night. This galaxy was breaking all paradigms. Gods of light were being born relentlessly. Chandra, the most powerful X-ray observatory ever built, would decipher the nature of the high-energy radiation emerging from its depths to confirm, as many suspected, the presence of a colossal monster. A guardian of darkness with unparalleled power. At the heart of the central galaxy, an invisible entity had to be lurking, a being capable of draining all the light in the universe. A realm stripped of all dimension that nevertheless might still be roaring. Like an unrelenting beast howling from that lost place in time and space. Like a dark well, everything was drawn toward its gravitational power. The boundary between the universe we know and the one hidden in the dark, indecipherable depths of a black hole, the Empire of Darkness. A place jealously concealed beneath its own shadow, where no beyond exists. A monster with a corrupted heart, enclosing the place where all paths end. The astronomical community was aware that Chandra's observations would reveal the existence of a supermassive black hole, responsible for the extraordinary X-ray emissions and even the high rate of star births in its extraordinarily active empire. Yet no one could have anticipated the grandeur, the true scale, of what they were witnessing. When Chandra completed its exhaustive mapping of that island of light 5.7 billion light-years away, the data was sent to a team at the Massachusetts Institute of Technology led by astronomer Michael McDonald for analysis. McDonald and his team were tasked with examining the X-ray emissions and identifying the accretion activity at the galaxy's core, where the supermassive black hole would be located. Chandra had provided detailed data on the hot gas at the galaxy's nucleus, showing that it was being drawn into a central region. By analyzing the velocity and distribution of the gas, alongside estimating the energy involved in forming cavities in the surrounding gas from jet emissions, they had everything they needed to calculate the black hole's mass. In 2012, they published the results of their research, unleashing a whirlwind in the community. They had just discovered the most massive black hole in history. Never before had we unmasked such a colossal king. Everything had led to the discovery of the greatest emperor of darkness in the universe.
Los resultados mostraron que el agujero negro en Phoenix A era de alrededor de 100.000 millones de masas solares. Es complicado poner en perspectiva lo que esto significa. Si redujéramos el Sol al tamaño de un huevo y quisiéramos juntar 100.000 millones de ellos en un volumen cúbico, necesitaríamos un cubo de 157 metros de largo, de ancho y de alto. Imagina las perspectivas de esto, pues estas eran las escalas en las que estábamos jugando. 100.000 millones de estrellas como el Sol, el 15% de la masa de toda la Vía Láctea, apiladas en un punto del espacio-tiempo, definido por la ausencia de sí mismo. Esto hacía de él el más masivo descubierto, superando a otros que históricamente habían luchado por ese título, como TON 618 y sus 40.000 millones de masas solares. Incluso él empequeñecía al lado del que se había proclamado nuevo rey de la oscuridad. Fénix A era 24.000 veces más masivo que Sagitario A, el agujero negro supermasivo en el corazón de nuestra galaxia. Pero no solo era masivo, era tremendamente grande. Se estima que el diámetro de su horizonte de sucesos es de 3.900 unidades astronómicas, o lo que es lo mismo, 100 veces la distancia entre Plutón y el Sol. Viajando a la velocidad de la luz tomaría 71 días completar su circunferencia. Todo el sistema solar podría descansar plácidamente en su interior. Habíamos descubierto un tesoro en medio de la oscuridad. Fénix A escondía las respuestas a muchas de las grandes preguntas. Era el momento de aventurarnos a ese lugar, mirar al monstruo a los ojos y contemplar lo que se esconde en las sombras.
The great kings of the universe exert an inescapable influence on the stars that, like subjects of these fierce emperors, remain anchored to the pull of that corrupted heart lurking within their depths. Supermassive black holes play a fundamental role in the evolution of the galaxies they rule. Hidden beneath the shadow of their own darkness, sheltered in the silence of the void seas, they may appear to live in absolute isolation. Yet through that invisible interaction that brings meaning to the universe, they become the conductors of an orchestra of light and matter. 5.7 billion light-years from our home, in a place and a past far removed, Phoenix A is drawing matter into its maw. Anything venturing too close to that boundary in space and time seals its own fate. It becomes trapped in the monster's grasp. But not all the gas and dust pulled in by the black hole falls into its singularity. Its high velocity and immense angular momentum cause the material to begin orbiting around it. A colossal accretion disk has formed. As the gas reaches relativistic speeds, the rotation of the black hole and the matter in the disk generate a very strong magnetic field. Trapped by its incomprehensible gravitational power, the material accelerates to speeds close to that of light, so fast that even the dark beast's gravity cannot contain it. All that power must escape. Guided by these magnetic lines, two streams of ultra-hot gas emerge from the black hole. Two jets of particles, traveling in opposite directions along its rotational axis, have escaped the gravitational prison. The beast, releasing all the power it has accumulated within its domain, emits vast amounts of energy across the electromagnetic spectrum. This explains the great luminosity and unusual X-ray readings at the heart of the cluster. Phoenix A is roaring from the depths of the void. The protons, electrons, and plasma making up these jets form pillars that stretch across vast distances, reaching hundreds or even thousands of light years. The most majestic creations of the universe. At the galaxy's center, where the black hole resides, the jets have an inhibitory effect on star formation. The streams expel material at high speeds and heat the gas near the monster, preventing it from cooling enough to condense into a dense cloud capable of collapsing under its own gravity to the critical point where the furnaces of creation ignite, where the temperature and pressure conditions allow nuclear fusion reactions to begin, and a star is born. Phoenix A is heating its nearby domain, preventing light from prevailing in its territories, battling against the birth of stars. But that victory is merely an illusion. The battle won in the galactic core has a ripple effect on the outskirts of the Island of Light. The gas swept away by the monster's roar travels to the galaxy's periphery. Acting like a cosmic fan, it pushes the interstellar material outward, compressing it and increasing its density. It creates the necessary conditions for the formation of cold molecular clouds, the first step in star formation. In that outer realm, Phoenix A is not heating the gas, it is compressing it. It allows the ashes of previous stellar generations to find refuge in the darkness. What began as a force of destruction has transformed into one of creation. Far from the beast's domain, thousands of stars are germinating thanks to the will of this dark god.
Esto explicaba no solo la gran emisión de rayos X, también la inusualmente alta tasa de formación estelar, nunca antes vista en un cúmulo tan masivo. Estaban naciendo unas 740 estrellas cada año. En comparación, en la Vía Láctea anualmente se forman apenas 7. La galaxia de Fénix A era una fábrica de estrellas, gracias a la violencia que se escondía en su corazón. Sabíamos que los agujeros negros supermasivos tenían una profunda influencia en la evolución de las galaxias que habitaban. Pero no fue hasta contemplar el esplendor de ese monstruo que entendimos la verdadera envergadura de la relación entre las tinieblas y la luz. Sin embargo, había algo en aquella historia aparentemente perfecta que no encajaba. Fénix A era demasiado masivo, tanto que duplicaba el límite teórico para la masa de un agujero negro. Todos los modelos cosmológicos coincidían en que la máxima masa que podían alcanzar era de 50.000 millones de masas solares. Dada la edad del universo y la eficacia para alimentarse del gas circundante, simplemente no había habido suficiente tiempo en el tiempo como para que un agujero negro creciera más allá de aquella masa. Pero ahí estaba Fénix A, multiplicando por 2 ese límite. No podía haber crecido tanto a través de la lenta captura de gas interestelar. Se necesitarían cientos de miles de millones de años para ello, mucho más que la edad del universo. Otro mecanismo desconocido hasta ese momento tenía que estar detrás. La inmensidad de Fénix A nos estaba demostrando que algo en nuestra comprensión de la evolución del universo estaba fallando, porque alguien tenía que ser el responsable de su masa. Tras muchos años de sospechas, los hallazgos en Fénix A evidenciaron que la masa de los agujeros negros supermasivos era uno de los grandes misterios de la astrofísica moderna. Un dilema que solo tenía 2 soluciones. O bien los agujeros negros nacieron como creíamos, pero crecieron muchísimo más deprisa de lo que sugieren los modelos actuales, lo que conocemos como modelo de semillas ligeras, o por el contrario, algo hizo que la primera generación fuera mucho más masiva de lo que hemos estimado, el modelo de semillas masivas. Pero solo podía haber una explicación. Muchos candidatos, pero un solo responsable. Teníamos que hallar la verdadera semilla de ese Dios.
The first hypothesis proposed to explain its seemingly inexplicable mass was that at some point in its life, Phoenix A committed one of the greatest acts of cannibalism in the history of the universe. A keeper of the darkness devouring the gods of light that dared to rise against it. In March 2023, a team from the Max Planck Institute for Astrophysics, led by Dr. Taiho Ryu, published a study on a peculiar cosmic event that could explain the existence of this hidden monster in the constellation Phoenix. When a star ventures too close to one of these beasts, the black hole's gravitational tyranny begins to unleash a storm in its core. As it approaches the beast's domain, the gravitational pull on the side of the star closest to the black hole is significantly stronger than on its far side. This difference in force is powerful enough to generate tidal forces that, to the star, feel like being dragged toward the black hole and deformed along a path leading inevitably to its doom. Sooner or later, the tidal forces become so intense that they overcome all others holding the star together. The monster's gravity tears apart a god of light, collapsing all the pillars that supported the star from its very core. Phoenix A has disintegrated an entire star, turning its ashes into a highly valuable source of nutrients. What scientists have named a tidal disruption event has just been completed. The remnants of the deceased star are trapped in the accretion disk, eventually becoming food for the beast. If Phoenix A repeated this process countless times, and if it had access to enough stars to feed on them ferociously, simulations showed that it could have defied the theoretical mass limit and reached 100 billion solar masses.
Sabemos que los agujeros negros en el centro de las galaxias pueden consumir estrellas enteras, pero estos eventos de disrupción de mareas son extremadamente raros. Estimaciones actuales hablan de un fenómeno cada 15.000 años para un agujero negro de 20 millones de masas solares. No hemos captado ni uno solo en Sagitario A y apenas hemos detectado 100 en galaxias distantes. Aunque puedan aportar materia a los agujeros negros, estos eventos son demasiado inusuales. No es suficiente para explicar la rápida acumulación de masa observada en los agujeros negros más grandes del universo temprano. De hecho, incluso suponiendo una densidad estelar en sus cercanías mayor que cualquier observada jamás, hay un límite a cómo de deprisa puede alimentarse un agujero negro incluso con un aporte infinito de gas. El límite de Eddington implica que la cantidad de materia que podría consumir estaría restringida por la radiación generada por este gas. Si el agujero negro alcanza su tasa máxima de acreción, la presión de la radiación expulsa el gas circundante. Phoenix A no pudo consumir materia a una velocidad ilimitada, porque el propio gas acelerando impediría que más materia cayera en él. Calculando cómo de deprisa podría crecer, incluso suponiendo que durante toda su vida se ha alimentado próximo a ese límite de Eddington, el resultado sigue siendo el mismo. No ha tenido suficiente tiempo en miles de millones de años como para llegar a su masa. En la acreción de gas no íbamos a encontrar la respuesta, y todos los caminos conducían al mismo lugar, a la más grande de las batallas del universo.
In 2017, the Hubble Space Telescope detected something unusual in a galaxy known as 3C186, an island of light resting 8 billion light-years away. The observatory confirmed the presence of an extremely luminous point, which astronomers immediately associated with a quasar. They had discovered an active galactic nucleus powered by a supermassive black hole, a discovery that might have gone unnoticed, joining the list of 1 million similar objects identified, if not for one critical difference. Every quasar discovered up to that point resided at the center of its galaxy, in the nucleus where the supermassive black hole rules its domain. Hubble's observation was peculiar because the quasar in 3C186 lay far from the galactic center, a staggering 35,000 light-years away. Finding a supermassive black hole so far from the core of its galaxy was already groundbreaking. But when further observations revealed it was moving at an extraordinary speed, alarms were raised across the astronomical community. A supermassive black hole, with an estimated mass of 1 billion suns, was traversing the galaxy at more than 6 million kilometers per hour. It became clear that although it once resided at the galactic center, something had hurled it into the void. Only one force could displace such a monster: to exile a god and condemn it to wander. 3C186 had to be the remnant of a galactic merger, a cosmic dance where two galaxies inevitably drew their hearts closer together, each hosting a beast, in a final chapter of destruction. Drawn by gravity toward a shared fate, the two kings met in the darkness. The final act in the story of two princes vying for the throne of a new kingdom, orbiting one another, gazing in silence, disturbing space and time around them, unleashing a storm in the very fabric of reality until at last, their corrupted hearts collided in a final embrace. The two monsters merged, releasing a tempest in the form of gravitational waves, subtle ripples in the fabric of space-time that may have been responsible for this exile. If the mass difference between the two supermassive black holes was significant, the burst of gravitational waves from the collision could have been emitted asymmetrically, with catastrophic effects. Like a hammer striking the pillars of nature, the gravitational waves would have been released in a single direction. This unimaginable release of energy, born of the most violent war in the universe, could have exiled the newly crowned king. The supermassive black hole resulting from the galactic merger, cast out by the echoes of the battle it had won, condemned to leave its kingdom, to venture into the far reaches of the eternal cosmic seas, an emperor whose memory will fade into the darkness.
Por primera vez disponíamos de evidencia de la fusión de agujeros negros supermasivos. Ya teníamos pruebas indirectas de que deberían ocurrir en las fusiones galácticas, pero siempre habían representado un desafío teórico para la astrofísica. A medida que se acercan, la densidad de materia en el entorno tiende a disminuir porque las estrellas y el gas cercano ya han sido dispersados por las interacciones gravitatorias con el sistema binario de los agujeros negros. En ese punto, los mecanismos tradicionales de pérdida de energía, especialmente las interacciones con las estrellas próximas, empiezan a ser insuficientes para acercar más a los agujeros negros. Hasta que finalmente, sin poder perder más energía, teóricamente quedan atrapados en una zona de estancamiento, algo que ocurre a una distancia aproximada de un parsec, o 3,26 años luz, algo a lo que llamamos el problema del parsec final. Los hallazgos en 3C186 cuestionan este dilema teórico, al ser una prueba relativamente sólida de la fusión de dos agujeros negros supermasivos. En tal caso, imaginando eventos de este calibre, tendríamos una explicación a cómo Phoenix A, como resultado de las colisiones con otros grandes monstruos, pudo aumentar tanto su masa. La pregunta evidente es cómo logró burlar este problema del último parsec. Un estudio publicado en enero de 2024, liderado por el físico Gonzalo Alonso Álvarez de la Universidad de Toronto, afirma haber hallado la solución al problema. La interacción con la materia oscura resuelve el conflicto del parsec final. Según los autores, si la materia oscura, con su halo teniendo una densidad mayor precisamente en el centro galáctico, interactúa consigo misma, podría crear una fricción dinámica que aceleraría la pérdida de energía orbital, y por tanto permitiría que los agujeros negros superaran la barrera del parsec final y pudieran fusionarse. De todos modos, incluso suponiendo que esta entidad lo resuelva, las simulaciones mostraban que el crecimiento por fusiones por sí solo no es suficiente para explicar una masa tan extremadamente grande como la de Phoenix A. Otro mecanismo tenía que estar jugando un papel, y quizás era precisamente en la materia oscura donde podíamos encontrar una esperanza.
With the discovery of supermassive black holes exceeding the theoretical mass limit, a once seemingly speculative theory emerged about an elusive fuel for these cosmic beasts. A hypothesis suggesting that these guardians of the darkness might secretly be feeding on dark matter. Since its formal discovery in the 1970s, we have known that galaxies are surrounded by a halo of undetectable matter that neither emits nor absorbs electromagnetic radiation, 9 times more massive than the visible portion of the island of light. This entity was named dark matter, the force responsible for giving gravitational cohesion to every galaxy in the universe. Despite near-universal consensus on the existence of this inescapable substance, the nature of dark matter remains a subject of debate. Numerous hypotheses have arisen to explain its properties, with WIMPs, weakly interacting massive particles, standing out as one of the leading candidates for constituting dark matter. This class of hypothetical particles would interact with ordinary matter only through gravity and the weak nuclear force, but not with light. A hidden face of the Standard Model that describes the gravitational consequences of this entity, and as a byproduct of the theory, could potentially explain the rise of cosmic monsters. Supermassive black holes might grow by feeding on these dark matter particles, which account for 85% of the universe's matter, providing a constant food supply to the beasts without depending on gas and stars. The idea of dark matter as fuel for these entities could explain their seemingly impossible growth if considering only the consumption of ordinary matter. Although the lack of a solid description of the interaction between dark matter and black holes kept the hypothesis in the realm of speculation, against all odds, we found the first evidence of this connection. In June 2022, a paper published in the Astrophysical Journal, led by physicist Maria Felicia de Laurentiis, claimed to have found proof that M87, the supermassive black hole at the heart of its namesake galaxy, was growing by consuming dark matter. 3 years earlier, we had obtained the first ever image of a black hole from M87. A portrait of this entity 53 million light-years away from Earth. Through the shadow captured by the Event Horizon Telescope, astronomers gathered highly precise information about the distribution of visible matter, the gravitational dynamics of the system, and the growth rate of the supermassive black hole, estimated by observing the radiation emitted by material plunging into its core. Researchers in the study discovered an apparent discrepancy between M87's accretion rate and the visible material supposedly fueling it. The black hole was growing faster than could be explained by visible gas and dust. This observation led them to argue that it was consuming dark matter. Simulations of M87's behavior revealed certain characteristics more consistent with dark matter's influence than with ordinary matter. Furthermore, they uncovered a peculiar connection that seemed too striking to be mere coincidence. On the one hand, correlation models between the mass of a supermassive black hole and the motion of stars in the galaxy showed that M87 was more massive than it should be, specifically by 2 billion solar masses beyond predictions. On the other hand, gravitational dynamic studies of Messier 87's galaxy, those revealing the distribution of dark matter in its invisible halo, showed an inexplicable deficit of dark matter at its core based on cosmological models of galactic evolution. The missing dark matter mass was approximately 2 billion solar masses, the same amount as the black hole's excess mass. The similarity between these figures led researchers to suggest that the black hole had grown by stealing and consuming those 2 billion solar masses of dark matter. Yet they acknowledged a significant problem with this concept. The proposed WIMPs that theoretically make up dark matter would, by definition, be particles interacting with one another, and with ordinary matter almost exclusively through gravity. They don't physically collide with anything, which posed a profound dilemma. Collisions are the only known physical process enabling matter in a black hole's accretion disk to stop orbiting and fall into the monster's core, thus adding to its mass. Only through particle impacts and the resulting energy exchange, where one particle loses all its energy and can no longer maintain orbit, can matter fall beyond the event horizon. But dark matter cannot collide. It cannot exchange energy with anything. If a black hole were to attract dark matter into its domain, all the particles would do is become permanently anchored in the accretion disk, peacefully orbiting a monster unable to pull them into its singularity.
La única forma viable de que atraviesen el horizonte de sucesos y contribuyan al crecimiento de la masa sería que las partículas de materia oscura se acercaran en una trayectoria muy específica, burlando el horizonte de sucesos y directamente hacia la singularidad. Pero los grupos que han simulado esto hablan de que este proceso explicaría solo el 10% de la masa del agujero negro. Y esto es en condiciones ideales, por lo que probablemente el porcentaje real sea mucho más bajo. Es más, es posible que las premisas del estudio no sean tan sólidas como los investigadores creían. Quizás esa correlación entre el movimiento de las estrellas y la masa del agujero negro se deba a una desviación estadística más que un sobrecrecimiento real. O puede que la distribución real de materia oscura en la galaxia no sea como la que predicen los modelos y que no haya esa masa perdida. Se necesitarán más investigaciones para profundizar en la relación entre los agujeros negros y la materia oscura. Pero por ahora, todo parece indicar que esos grandes monstruos como Fénix A no crecieron utilizando la materia oscura como esa especie de fertilizante cósmico. Las teorías del modelo de semillas ligeras terminaban, y si no había nada que explicara cómo crecieron tanto, teníamos que reescribir su nacimiento.
No known process in the universe could explain how supermassive black holes grew so large and so quickly from the first generation of dark princes. The logical step, therefore, was to reinterpret the theories about their birth. The monsters born from the collapse of a massive star, the only process we believed allowed the germination of a black hole, were no longer sufficient. We needed to find a new cradle for these beasts, one that would allow them to flourish with a much greater immensity than the sacrifice of a single star. In 1974, just 3 years after the confirmation of black holes' existence, theoretical physicist Stephen Hawking and astronomer Bernard Carr wondered if only the gravitational collapse of a star reaching its end could fracture the fabric of space-time. At the point of infinite density we call singularity. The corrupted heart of one of these entities. The British scientists developed a hypothetical scenario, an alternative birth that would allow them to germinate in the deepest darkness before the era of the first stars, in the early whispers of the Big Bang. Monsters emerging from the extreme density of the universe at the dawn of reality. The primordial black holes had just been conceived. Under their theoretical framework, the densities in the opaque plasma ball of the primordial universe, in the moments after the Big Bang, were so high that tiny fluctuations in the distribution of matter could have led to regions where the architecture collapsed directly into a singularity. The first black holes had germinated. Heralds of the birth of the cosmos, beasts as old as time itself. The first generation of that dark lineage. The parents of all the princes of darkness. Immutable guardians of space and time, who, if they existed, would have been the seed of the great emperors. Hawking and Carr's theory of primordial black holes, though attractive, has remained for decades as just that. A plausible hypothesis with no observational evidence to support it. But this may have just changed. In 2023, the James Webb Space Telescope turned its gaze to a bell 2744, nicknamed the Pandora Cluster, a galactic cluster of several hundred galaxies located 4 billion light-years away. Its immense gravity acts as a gravitational lens, distorting space and magnifying and clarifying the images of nearly 3,000 distinct galaxies resting in the most abyssal corners of the universe. Thanks to this, James Webb discovered 11 galaxies lying more than 13 billion light-years away, a snapshot of how they looked a little more than 500 million years after the Big Bang. Realizing these were glimpses of a universe in its infancy, they sought to determine if any of these galaxies contained a supermassive black hole at their core. The Chandra Observatory mapped that region, finding X-ray emission consistent with the presence of one of these beasts in just one of the 11. It was named UHZ-1, a quasar with a mass 6 billion times that of the Sun. It was more massive than the visible portion of its galaxy. The findings in UHZ-1 were extremely rare. Normally, supermassive black holes at the centers of galaxies have a mass roughly 0.1% of their host galaxy's total stellar mass. In the case of UHZ-1, the black hole represented more than 150% of the galactic mass, a highly unbalanced and unprecedented ratio in the observation of the universe. It was the first example of a new hypothetical class of celestial object called OBG, short for overly massive black hole galaxy. It was an unusually large black hole in proportion to its galactic environment. A discovery that revived the theory of the British scientists. The existence of UHZ-1 was only possible if its seed had originated from one of those monsters born from the direct collapse of the plasma in the primordial universe. The possibility of having found the first evidence of primordial black holes was being raised.
Al evitar la fase estelar, estos agujeros negros de colapso directo podrían haber comenzado su vida con masas de hasta 100.000 veces la del Sol. Ya habrían nacido como agujeros negros supermasivos, y a partir de ahí, con la tasa de acreción normal, se podría explicar que con la edad del universo se llegara a algo tan inmenso como Fénix A. Además, esta concepción solucionaba otra de las grandes incógnitas de la cosmología. Hemos encontrado agujeros negros en el rango de las 10 a las 100 masas solares, que corresponden a los agujeros negros estelares, y de 100.000 a las 100.000 millones de Fénix A, propias de los agujeros negros supermasivos, pero hay todo un rango intermedio en el que no hemos encontrado nada. No hemos hallado ni un solo agujero negro que tenga entre las 100 y las 100.000 masas solares, todos están por debajo o por encima. Suponiendo que aquella primera generación arrancó próxima a las 100.000 masas solares, podemos explicar que no hayamos encontrado nada en ese rango intermedio, porque los supermasivos no nacieron del colapso de una estrella. Son los herederos de esos agujeros negros primordiales. Aún así, no está claro qué condiciones específicas permitirían ese colapso directo del plasma primigenio en lugar de la formación de una estrella. Aunque la teoría sea prometedora, no podemos sentenciar nada. Quizás simplemente UHZ-1 sea un caso único. O tal vez sí represente una realidad, pero no a través de esos agujeros negros primordiales, sino de unas estrellas que en su corazón atesoraron a las primeras bestias. Quedaba un último escenario, para dar con la semilla de Fénix A.
At a time when solving the paradox of supermassive black hole mass had been established as one of the great priorities of the astronomical community, theoretical astrophysicist Mitchell Bagelman offered a captivating solution to the problem through the conception of gods who may have reigned at the cosmic dawn. One of the most important predictions of the Big Bang Theory is that the early universe only contained the lightest elements, hydrogen, helium, and traces of lithium that were almost irrelevant. All those heavier elements, described as metals in the astronomical context, did not emerge at the beginning of time. They were conceived later, in the inner furnaces of the gods. All of this led to the inevitability of a first generation of stars very different from those that inhabit the seas of the cosmos today. An ancient stellar lineage that rose when the universe had no metals, formed purely of hydrogen and helium. The first stars of the universe, those in whose hearts light first germinated, were baptized as population-thirst stars. 100 million years after the birth of space and time, the Dark Era ended, witnessing the rise of the first factories of complexity, the moment of the first lights. A cosmic dawn when the first stars were born to mark the beginning of a new age. In the hydrogen and helium clouds from which they emerged, without heavy metals, the cooling capacity was extremely low. The gas had no time to fragment into smaller cores. The collapse occurred on an immense mass scale. Everything condensed into a single titan. Population 3 stars were immense giants, thousands of times more massive than the Sun, larger than any star from later generations, incapable of exceeding 150 solar masses. Colossal, extremely luminous and hot, shining like 10 million suns, and radiating an imposing blue color. The largest and most powerful stars that have ever existed. But they were born with a marked destiny to live fierce and short lives. In a suffocating struggle for survival, unable to withstand the hellish power they harbored in their hearts, the mass with which they were conceived was a death sentence. With uncontrollable fury, Population 3 stars quickly consumed their hydrogen, a moment when the core begins to collapse on itself and heat up, something that the star responds to by forging increasingly complex elements, atoms with a higher number of protons. The first heavy elements in the history of the universe are being molded in their depths. But in what is, on a cosmic scale, a sigh, the stellar poison was born. When iron atoms are forged, everything changes forever. Their fusion, for the first time in that sequence, does not release energy. An iron heart has been sculpted, and the star has poisoned itself. There is nothing left, no nuclear pressure in its depths, to prevent the collapse. Despite fighting with all its strength until its last breath, the star has lost the battle against gravity. In what could barely be 100,000 years, Population 3 stars perished in the most violent phenomena of nature. Gravitational collapse pushes all the trillions of tons of gas toward that iron core. The pressure grows exponentially until an explosive wave is triggered, expelling the outer layers. The star has died in the form of a supernova. All the elements it had carefully guarded in its heart have been released. And amidst that devastation, the gates of the underworld were opened. Something remains in the darkness, a corrupted memory of its existence, an unexpected sequel to its sacrifice, a ghost in the shadows. The first black holes have germinated. Darkness has declared war on light once again. With the theorization of Population 3 stars, that first stellar generation much more immense than those that inhabit the universe today, we thought we had before us an explanation for the origin of supermassive black holes. If these first monsters were conceived after the collapse of stars hundreds of times more massive than those of today, it was tempting to think that their starting point was enough to explain the masses observed billions of years later. But although it seemed a promising hypothesis, we quickly saw that even with the sacrifice of those colossal stars, we could not explain the mass of supermassive black holes like Phoenix A. Still, trusting the premise that the answer had to lie with the mothers of all stars, Begelman rewrote the end of their lives to make sense of the nature of the beasts. The American physicist proposed the possibility that those first stars, thanks to their titanic mass, could resist the collapse of their cores. If somehow they withstood the supernova explosion in their depths, suddenly everything fit together. He was conceiving a new type of celestial body, theorizing that after a failed death and incomplete sacrifice, the core of those stars was inhabited by a cosmic parasite. The hypothesis of what he himself called quasi-stars was born. Stars that between life and death, guarding a black hole in their heart, could shape the fate of the universe. Not even the explosion was enough to break them. The star survived its own death. It contained a supernova. The heart was fractured, the god remained alive. But something had changed in its depths. That parasite had sprouted. A dark beast was trapped inside. A tiny black hole trapped inside a star with a diameter like that of the solar system. But the power of that entity is unrivaled. It is going to devour its mother star. Everything it is cannibalizing begins to orbit around it, creating an accretion disk in the dead core of the star. The same process as in conventional black holes, but now everything takes a different path. In those that roam freely through space, the very heat of the disk, due to the friction and collisions of particles at speeds close to light, was what restricted the amount of matter they could devour. The ultra-hot material releases radiation that physically pushes the food away from the monster's jaws, putting a brake on the black hole's growth speed and thus creating the limit that prevented a monster like Phoenix A from existing. But it was here where quasi-stars saved us. The black hole trapped in their heart would behave very differently, and suddenly all those restrictions disappeared. Subjected to the pressure of thousands of suns, with the outer layers of the star pushing all the matter toward the gates of darkness, the radiation from the accretion disk is no match for the power of the star. It has everything within reach. There is nothing preventing it from feeding. The black hole overcomes all the limitations it would have outside of that prison. A feast of stellar material. For a few million years, the star is consumed from within by the parasite. The more it grows, the more it devours, the more radiation it releases, and the more it expands the star, causing it to reach a size 30 times greater than the entire solar system. But little by little, with the nuclear fusion reactions having been turned off long ago, kept in a tragic state between life and death by the radiation of that trapped monster, the star approaches the end of its life. When the temperature drops below 3,700 degrees, its story ends forever. At that point of no return, no hydrostatic equilibrium can be sustained. The star dissipates instantly, in silence. In the cold void of space, everything fades in peace, leaving a cruel air to its existence. After so much time in that prison of light, the guardian of darkness has been freed, and the seed of supermassive black holes planted in the midst of the shadows.
Hasta ese momento creíamos que los primeros agujeros negros no podían tener más de 100 masas solares. Los concebidos por las cuasiestrellas podrían alcanzar fácilmente las 100.000. Con ese punto de ventaja en el momento de ser liberados sería relativamente sencillo, o al menos coherente con los modelos actuales, que con la edad del universo alcanzaran una masa tan grande como la de Phoenix A. Desde su formulación teórica en el año 2006, las cuasiestrellas siguen siendo una de las pocas teorías en ese modelo de semillas masivas que explican el origen de los agujeros negros supermasivos. El problema es que no deja de ser una teoría, no hay evidencia observacional de su existencia, y aunque hubieran existido, detectarlas sería extremadamente difícil. Si las cuasiestrellas existieron, lo hicieron en una era muy temprana del universo, entre 100 y 500 millones de años después del Big Bang. Una edad tan ancestral que por la expansión del espacio, su luz habría caído al espectro infrarrojo. La única esperanza de dar con indicios de su pasada existencia la tenemos en James Webb, pero por ahora no hay datos que empujen al optimismo.
In the context of the massive seed model, the theory of quasi-stars and primordial black holes have given us scenarios where black holes are born with much larger masses than those conceived by the conventional star death mechanism. But the validation of these hypotheses still seems to rest in a distant future, and it is even unclear whether they can explain how they continue to grow at such high rates. On the other hand, within the framework of the light seed model, the ingestion of stars, with those tidal disruption events, mergers between these monsters and the absorption of dark matter, may help explain the speed of their growth, but they lack the necessary timescales to explain the massiveness of those observed in the early universe. These are insufficient hypotheses, and in some cases not even proven in terms of scale and time.
El misterio persiste y es probable que sea una combinación de varios de estos procesos y quizás de otros que aún están por descubrir, lo que finalmente resuelva el enigma de los agujeros negros supermasivos. Lo único que ahora mismo está claro es que Fénix A, a través de su inmensidad inexplicable, nos ha motivado y nos seguirá motivando a echar nuestra mirada al cielo, a sumergirnos en los imperios de oscuridad, para escuchar al universo contar su historia.
Those great emperors, as immortal heirs of princes who began the battle between light and darkness, hold the answers to the deepest of questions. As a sign from that universe which may have only found in us the way to understand itself, Phoenix A has become the precursor to a new era. And driven by that unyielding will to glimpse what lies beyond the horizon, we will dive into those realms that break everything we thought we knew. In the corrupted hearts of the great kings of darkness lies the beginning, and the end of everything. Even though we may not know what we will find, it is our duty to keep looking those monsters in the eye